Okay, now let's talk about how to do a partial fraction decomposition of a non-repeating irreducible quadratic factor. An irreducible quadratic factor is one that can't be factored. And an irreducible quadratic factor will have a decomposition term of this form here, where I need ax plus b in my numerator. And let's take a look at an example. Here I have a rational function. Just like before, I need to factor my denominator as far as I can, and this is completely factored over the real number system. I have a non-repeating linear factor and a non-repeating irreducible quadratic factor. This factor cannot be factored any further. Okay, so I'm going to take my rational function and I'm going to have my partial fraction decomposition term for a non-repeating linear factor and a partial fraction decomposition term for my non-repeating irreducible quadratic factor. And the question is, I need to find a, b, and c such that this side of the equation equals this side of the equation. Okay, so here it is. There's the equation I just showed you. And just like before, I'm going to multiply both sides of the equation by this entire denominator, which is what I've done right here. And just like before, this denominator cancels with the multiply. I'm going to distribute this in. When I distribute it over here, the x plus 5 will cancel, and I'm going to get a times this factor right here. There it is. And when I distribute it to the second term, I'm going to get bx plus c. Well, this factor will cancel with that factor. I'm going to get bx plus c times the quantity x plus 5. There's bx plus c times quantity x plus 5. And now I just need to distribute in and do double distribution or FOIL on this, and I get the expanded term here. I do not have a coefficient of x squared, or rather I have, it's 0. So 0 has to equal the coefficients of x squared. 0 has to equal a plus b. My coefficient of x, oops, I did a 3, okay. My coefficient of x is 1 over here, and I have a 2a plus 5b and plus c, so 1 has to equal 2a plus 5b plus c, and my constant term is negative 3, and that has to equal 3a plus 5c. So again, I have a system of 3 equations in 3 variables, pardon me, and I can solve this system using any method available to me for solving systems of equations. Again, elimination, substitution, matrix methods, they all work. Okay. When I do that, in this case, I'm going to get a is equal to negative 4/9, b is equal to positive 4/9, and c is equal to negative 1/3. So plugging in, I'm going to get negative 4/9 for a, positive 4/9 for b, and negative 1/3 for c. And this is a partial fraction decomposition of this rational function here, but I can make it look a little bit simpler if I factor a factor of 1/9 out of both of these terms. There's my 1/9. You can see that the partial fraction decomposition looks a little bit simpler here. Every time I do a partial fraction decomposition of a rational function, basically what I'm saying is, if I add these two fractions together and multiply by this term out here, in other words, do this operation, I'm going to get this function back again. Now there's one more consideration we have to take a look at here, and that is, what happens if I have what we call an improper rational function. An improper rational function has the degree of the numerator higher than the degree of the denominator. And to do that, I'm simply going to do the division using polynomial long division. Anytime I do a division, the dividend divided by the divisor will equal the quotient plus the remainder divided by the divisor. So when I do this division, I get this for a quotient, this for a remainder, here's my divisor, and this piece right here is the piece on which I'm going to do a partial fraction decomposition.